Have more examples of butene. So here basically we have the double bond. So we know the structure belongs to alkene. The name has to end up with ene. We have four carbons in the straight chain. So it's butene. And then I have the double bond on the first carbon. So it becomes one butene. The same is the similar structure, but this time the double bond is on the second carbon. So it becomes two butene. And here, basically, I have another structure, which I have the double bond. So I know it belongs to alkene. Name ends up with ene. But this time, the longest chain has three carbons. So it's propene. And then I have a methyl group as a branch. So it becomes methyl propene. And you cannot have different form of the methyl propene. So we don't need really to say it's a it's a two methyl one propene. Basically, there is no other way. So all the methyl propenes will be two methyl one propene. So in this case, if you don't mention the numbers, it's okay. But in these cases, we have to mention the positions because there are so many different possibilities. Okay. In addition to these branches, there are some branches which we call it stereoisomers. Okay, these stereoisomers, these are basically the ones that you can only see under the microscope. Okay, so even the location of the bonds are the same and the location of the branches are the same, but the configuration in the 3D space sometimes leads to different physical and chemical properties, like different boiling points. In the case that the like in these two structures, they are both the same. If we want to name them without the having the 3D macroscopic image, they will be named exactly the same. Okay, so they will be both 2-butene. Okay, so they are 1, 2, 3, 4. 1, 2, 3, 4. Only one double bond, so it's butene, and the double bond is on the second carbon, so it's 2-butene. However, if we look at under the microscope, we see the cis 2-butene is such that these two carbons they come up together instead of being away from each other. So when they come together, they generate more of a protected area, and then they are more stable than if they're just simply around. So this double bond is somehow protected here, more protected here than this structure. So cis are generally more stable than the trans structures, but this is something that we just see under the microscope. So you really don't need to worry about them at this point. Okay. So alkenes properties, the physical properties are very similar to alkanes. However, these structures are more reactive, okay, because of the presence of the double bond. And the reaction becomes the elimination of the double bond and converting to the single bond. Okay, so alkenes, when they go to the reaction, they will first lose their double bonds and they becomes alkanes. And then if there are branches, then the second reaction will be elimination of the branches. In the case of double bonds, we could have two double bonds, okay, or three double bonds. If you have two double bonds, then the structure belongs to alkadienes, okay. So again, these are like alkenes group, okay. So the name ends with ene. However, since we have two double bonds, or in the case we have three double bonds, the name becomes butadiene or pentatriene. So diene or triene becomes at the end of the name. Since we have two double bonds, it becomes diene, and then here I have three double bonds, it becomes triene. And if I want to name them again, I see there is a double bond. I know this belongs to alkenes, so the name ends up with ene. I have two of them, so it's diene. I have four carbons in the straight chain, so it's butadiene. And then I have the double bond, the first and the second carbon, so it becomes 1,2-butadiene. In this case, again, I have a double bond. I know then it belongs to alkene. The name ends with ene. I have two of them, so it becomes diene. I have 1, 2, 3, 4 carbons in the straight chain, so it's butadiene. And then I need to number the carbons. It doesn't matter which way you go because both of them they have the same number on the first carbon, so it becomes 1, 2, 3, and 4. So I have 1 and the 3 butadiene. In this case, again, I see the double bond. The name ends with ENE. I have three of them, so it's triene. And then I have five carbons in the straight chain, so it's a pentatriene. And then the locations are 1, 2, and 3. So 1, 2, 3 pentatriene becomes the name. The alkadines are most of the time called diolefins, and the alkatrines calls the triolefins. As I said, the alkanes are paraffins. Alkanes are paraffins because they are not reactive. Alkenes are called olefins. Alkadines are diolefins, and alkatrines are triolefins. These are the industrial names. So in the industry, nobody calls these alkanes. They say, hey, the paraffins group or olefins group. So when they say paraffin, they refer to alkanes. When they say olefins, they refer to alkenes. When they say diolefins or triolefins, they refer to alkadines or alkatrines. So that's a different like industrial naming. But based on the IUPAC, these are alkanes, alkenes, alkadines, and alkatrines. Okay, just to remember, if you heard something like diolefins and triolefins and olefins, it's basically the same as alkenes that we taught in the class. Okay, so that was the second homologous series. The third homologous series are alkyne groups. Okay, alkynes are the hydrocarbon components with the triple bonds. Okay, so the general formula for alkynes are CnH2n-2. Okay, so for every number of carbons, the number of hydrogen is 2n-2. Okay, so if you have a carbon number of 2, then it becomes C2H2. 2 times 2, 4 minus 2, it's 2. So ethyne is the first member of the alkyne group. So as soon as I see the triple bond, I know this belongs to alkyne group. So the name has to end up with YNE instead of ENE in alkenes or ANE in alkanes. So alkynes, the name ends with YNE. As soon as I see the YNE, I know this belongs to alkyne group. Or as soon as I see the triple bond, I know the name has to end up with YNE. I have 2 carbons, so it's ethyne. Okay. So the physical properties are like the alkanes and alkenes. However, since they have triple bonds, they are more reactive. So this chemical reactive would be to break these triple bonds and make it like alkanes, having it as a single bond. Some examples of alkynes. Here, triple bond, the name should end up with YNE, and I have the 2 carbons, so it's ethyne. I don't need to number the carbons because it doesn't matter, there's only one type of ethyne. The same as propyne. Again, I have triple bond, so the name has to end up with YNE. I have 3 carbons, so it's propyne. However, if I go to the longer chains, then I need to number the carbons and mention where that triple bond is. Okay, so I see the triple bond, so the name has to end up with YNE. I have 4 carbons in the straight chain, so it's butene, and I have the triple bond on the first carbon, so it becomes 1-butene. Here again, I see the triple bond, so YNE. I have 4 carbons, butene, and the triple bond is on the second carbon, so it's 2-butene. Okay, a very similar, approach. It's just we just look at the bondings. It's all single, that belongs to alkanes. If there is a double bond, that belongs to alkenes. If there's a triple bond, that belongs to alkynes. We find the longest chain, and then we number them from the end which is closest to the branch, or the double bond, or the triple bond. Okay, so these are the alkyne groups. Okay, but however, in many hydrocarbon components, to generate these very long chains, it's not always easy to have all these straight chains. Sometimes, as we show in the 3D, in the case of cis structures, these structures, they try to bend, and then they generate this cyclic structures. Okay, and as soon as they generate the cyclic structures, the behaviors will change. Okay, therefore we will have another homologous series, which we call them cycloaliphatics. So the cycloaliphatics are the structures which they are circular. They show some cyclic structures, okay? And this cyclic structure could have the cycloalkanes or cycloalkenes, okay? So the cycloalkanes are also known as naphthenes in the industry, okay? So cycloalkanes are basically all single bonds, but in the form of the cyclic structure. Cycloalkenes are all, or they will have a double bond, but again in the cyclic structure. Cycloalkadienes are basically, again, they will have two double bonds, but in the cyclic structure. Okay, so this is another homologous series that we are going to look. The general formula for cycloalkanes are CnH2n. Okay, so as I said, these are structures which they show like a cyclic structure, and they all have single bonds. For example, here I look at this structure, they're all single bonds, so I know this belongs to alkane. The name should end up with A-N-E. However, since this is and I have 3 of the carbons, so it's propane. However, since the structure is cyclic, I call it cyclopropane. The same here. All single bond ends with A-N-E. I have 1, 2, 3, 4 carbons, it's butane. But since the structure is cyclic, I call it cyclobutane. Or here, I have all single bonds, ends with A-N-E. I have 1, 2, 3, 4, 5 carbons, so it's pentane. In cyclic structure, I call it cyclopentane. Okay. Some more examples. Again, all single bonds, names end with A-N-E. 1, 2, 3, 4, 5, 6 carbons. It's hexane. In the cyclic structure, I call it cyclohexane. And this is cyclopentane. Sometimes in cyclic, exactly like the other structures, we don't show the hydrogens, we just show the carbons. And in the cyclic structures, you can also just ignore putting the carbons. You can just show this. So this is basically, I know this is carbon. I have all single bonds end with A-N-E, and I have 1, 2, 3, 4, 5, 6. So it's a cyclohexane or cyclopentane. And in this structure, again, these cyclo structures, they could also come up with branches. So again, I look at this, all single bonds, the name should end up with A-N-E. Main structure has 1, 2, 3, 4, and 5 carbons, so it's pentane. It's a cyclic structure, so it's cyclopentane. And the first and second carbon, it has the methyl group. So it comes 1, 2 dimethyl cyclopentane. Again, we number them from the end, which is closest to the branch. So this is the closest. And with the end, and I go in the direction that gives you the lowest number to the branches. So I don't go this way. So it's 1, 2, 3, 4, 5, not 1, 2, 3, 4, 5. Okay. So I go from this side. If I go from this side, I have 1, 2 dimethyl cyclopentane. Okay. And you should expect a very similar, nomenclatures for your exams. So these cyclic structures, as I said, they can come together and generate a very long chains, okay? Like these structures, okay? Which called dicholine or bicyclodecane, okay? Since there are 2 cycles, we call it bicyclo. Again, all single bond, the name ends with A-N-E. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so it's decane. And since there are 2 cycles, I call it bicyclodecane or bicyclooctane. Okay. I also have cycloalkenes and cycloalkadienes. So in the case of cycloalkenes, I see the double bond. So if I have 1 double bond, that belongs to cycloalkenes. Okay, I have a double bond. I know the name should end up with E-N-E. I have 5 carbons, so it's pentene, and the structure is cyclo, so it's cyclopentene. Here again, I have 2 double bonds, so I know this belongs to alkadiene. So I have double bond, ends with E-N-E. I have 2 of them, so it's diene. I have 6 carbons, so it's hexadiene, and then I need to mention where those are located. They're on first, second, and third. So on 1, 2, and 3. So it's on the first and on the third carbon. So I have 1, 3 cyclohexadiene. Okay, and I'll continue this on the next part of the lesson 1.